Okay, thanks for that. In the interest of keeping vaguely on time, I'll start as I've got too many slides, as
Introduce yourself.
I was convinced that the talk was originally going to be longer, so I was frantically adding more and more slides, and then I saw the length of the talk, and then I've been frantically taking them back out. So partly, I think that was staying up too late to watch the USA game last night. Okay, I'm Andy Lupini, and I'm from Oak Ridge National Lab. I'm at the Centre for Nanophase Material Sciences, which is a user centre supported by the DOE, and I'm going to talk about various things in STEM. Okay, start with, have you ever seen a diffraction pattern formed by a single electron? Now you have. Not very exciting, is it? So, okay. Maybe if you had another electron, it will get more interesting. No, still boring. Okay, let's keep adding some electrons in, and you can see something starts to build up. So the point I'm sort of laboring here is really this is the young slit type of experiment where you can see that you have an image which at the end you can only really explain by thinking about it as a sort of wave optical approach, and you see how it's being built up single electron by electron from discrete particles. So I'm going to talk a bit about how we got there. So if there's a motivation for this talk, it's from Richard Feynman's famous talk where he put out some challenges, and he said, what's the thing that we could do as physicists that would most benefit other scientists? And his answer, interestingly enough, was to make the electron microscope better. And another challenge he put out was to rearrange atoms, which I think you've just seen from Kevin. So that's really what this talk is going to be about. Okay, so I'm going to be talking about mostly scanning transmission electron microscopy. So if it was longer, I think I'd go through this in a bit more detail, but you can see a stem which I've drawn the right way up this time. with the source at the bottom and the detectors at the top. Really, the important thing is that the exciting electron optics are mostly before the sample, and we form a very small probe which is about the size of an atom. We generate an image by moving that probe over the sample, and primarily we look at, say, the Z contrast image, which is the high angle scattering. The scattering out to high angles is roughly proportional to the atomic number or square of the atomic number. And so you can tell what you're looking at, even if you don't really know. You can tell where the bright atoms are and where the lighter columns are. And I should say, if you're only recording the scattering out to high angles, there's a lot of other information that's essentially unused. And that's really what we're going to be talking about. You could take spectra, and perhaps an important thing for this workshop is that the aberration corrector, which is the thing I would normally talk about, but not going to cover here, makes the electron microscope, which is already pretty complicated, it makes it even more complicated. So you're going to need some sort of computer control. So the first real images of atoms were actually taken in the 1970s by Albert Crew and some co-workers. And there are some interesting things. If this workshop had been about 100 years ago, we might have had quite an exciting debate on whether atoms exist or whether they're just a convenient accounting device to keep the chemists happy. And when I went back and looked, it turned out some of the first papers, they actually weren't just images of atoms, they were movies of atoms. And that's because they were recording these frames on film. And so naturally, they got a whole bunch to try and make sure they got a good one. And then they could put these things together as sequences, and you could see atoms moving. And here's an example of this sort of process in a modern electron microscope. So here we weren't trying to control the atoms at all, unlike the previous talk. We were trying to get multiple images of the same sample to try and improve the statistics to figure out exactly what it was we were seeing. How many atoms are there in each column? What depth is this dopant inside the crystal? And when you start trying to do this, you see it moves around and it's jumping around. There's kind of a pattern to the movement as well. So this sort of work led to a very exciting article by one of our hosts here, which is the Atom Forge, where he pointed out that you can actually use this kind of technique to pick and place atoms, kind of like they were doing in the STM. You can move single dopants about, but the advantage is you're doing this below the surface in a device, and as you've just seen, you may have something that you can actually take out of the electron microscope and it won't be destroyed the second you expose it to air. So this was as far as we could get before the sort of automation that Kevin showed. So this is an example. We're trying to do this for quantum computing applications. Can you try to position single dopants inside a crystal? So this is, in this case, it's actually bismuth atoms inside silicon, and we had to tune the energy of the electron microscopes up quite carefully so that we could still have enough energy to move dopants around, but not enough that we're just like melting through the crystal. And this was actually done by postdoc power. So you can see the drawbacks of doing it manually. Why you need that kind of automated process that you just saw is that you're using the same beam, in this case, to image as you are to manipulate. And so you're getting a lot of unwanted damage and a lot of unwanted movements. And that was about as far as we could get before then. And so then that would be an introduction to Kevin's talk. But now we are going to turn instead to how else could you improve the electron microscope? So the other way that we're working on a lot at the moment is to make better detectors. And so one of the steps towards this is, instead of just having a single detector like that, the HADAF high angle detector recording and scattering out to high angles, you could perhaps have just left and right. And so this is basically differential phase contrast. So if you think about shooting a beam of electrons through your sample and then it's deflected by electric or magnetic fields inside the material, then you're going to have more of your beam hitting a detector on one side or the other. And of course, any solid is just an array of atoms which are effectively point like potentials. So there was a lot of good work, particularly by Naoya Shibata about 10, 15 years ago. Well, you can go further in this direction. So, okay, imagine instead of just having like a left, right, or up, down, you have a pixelated detector. So you record that whole diffraction pattern, and then you can integrate over whatever parts of the scattering distribution you like. So why would we do that? Why wouldn't we just record that whole bright field disk? Why is it that no one, until perhaps recently, really does much bright field STEM? And the answer is it's much less efficient than doing it in TEM, because you can only record a small fraction of those images if you want to get a nice coherent image. So this is just a derivation from the 70s, when people used to have to do maths instead of just putting it into a powerful AI. And this shows that it's the limitation spatial coherent. You start to get an incoherent sort of image, which is not what you want when you're doing bright field TEM. So, okay, so what you want is, you want a universal detector, and then you want a file format which is supported by Microsoft more than a few days after you use it. But anyway, so that animation doesn't play, but this is a graphene sample, and you scan the beam over it, you look at this scattering on the detector, you record it, you build up this massive data set where you record that whole scattering distribution for every probe position, and then you can integrate over it. You can start to form different sorts of images, your high angle dark field, annular bright field, different sorts of bright field image, and your differential phase contrast. Instead of by having the segmented detector, you can just numerically integrate to find this sort of thing. Okay, why would we want to do this? So you're trying to maximize as much information as you can get out of each electron. And so one way I like to think about this is, imagine your data now is some sort of four-dimensional cube where and you can process that in different ways. And there's, of course, the tychography and those sort of methods that you heard about from Colin Ophus a few days ago. So I like to sort of think of that. So if you have an image and you Fourier transform it, you get a diffractogram. But now remember, we've got this sort of multi-dimensional cube where each of these pixels really corresponds to some sort of integration over a plane. And you can do the same with your Fourier transform. Each spot in that represents some sort of plane in the transformed hypercube. And so you can start to back out the phase of your beam, and you can get your image aberrations out quite directly from this sort of thing. Okay, you can do other little games with this, some of which are perhaps easier to understand. So here, what I've done is I've laid out a bunch of images and I've set them out in a square on a detector corresponding to which part of the detector I was integrating over to generate that image. And each of them is a slightly different image of the sample. And by the principle of reciprocity, this is exactly the same as tilting your illumination in STEM. And each of those images is shifted a little bit, which we pointed out that you can use those shifts, again, as another way to measure your aberrations, which is kind of a nice way to control your aberration corrector. And you can do various other sorts of games with this. So in that example I just saw, this was an image of gold particles on a carbon film. There was a little bit of defocus. So your ADF image is rather blurry. But if you take a single pixel on your detector and use that to generate a bright field image, you get a nice, sharp, coherent bright field image, but it's rather noisy because you're only recording some time, or you're only using, I should say, some tiny fraction of the electrons that interacted with your sample. So if you then use many pixels, again, you get a nice blurry bright field image. But remember, each of those pixels was looking at the sample from a different angle. So there's a small shift. And so you can numerically reverse those shifts, and then you can get an image which is, it turns out actually to have higher resolution than an axial bright field image, but it's sort of a, digital composition. So we had big questions as to whether these meant anything, but I should point out we were actually the first group to show those, and then they were later popularized as tilt-corrected bright field image because each of those pixels is at a different tilt. It gives you a shift at the sample. So I would perhaps think that unless you're correcting some of the other effects, you could perhaps call it more correctly shift corrected, but then you can play games of starting to correct the other aberrations or use it in a tachographic reconstruction. Okay, so having seen that there's a lot more information in those recorded scattering distributions, maybe the next thing you want to do is go faster. So over at CERN, they've been developing these very high-speed detectors for tracking particles that come out of the various particle accelerators. And there's a new generation of those which are really well suited to electron microscopes because they're able to count fast enough that they can keep up with every electron in our beam. So, of course, that was how I generated that pattern that was building up at the start, is by using one of these detectors in an electron microscope. So there is a commercial product which has just been released now, which is called the Timepix 4 from Quantum Detectors, and it's kind of interesting because it can record single electrons down to about a 200 picosecond time resolution. We got the first one of these in the US, and we had to design a little extension for the electron microscope, and we added some pumping and some supports to our EO spectrometer, and we were able to integrate this in with the NEON system. You can see there this big silver box actually is this retractable detector module, and when it would be hooked up, that you can see there's a little flange that we had to design so we could put this into the column, and then there would be some fiber optics coming out here to deal with the amount of data that was coming. And So when I say the amount of data, it's really is, it's just data. It's not frames. So it's not like a conventional 4D camera where you just get many frames very quickly. You just get a list of events. And it turns out to get down to this few picosecond timing resolution, it's pretty difficult because if you think about it, just the time it takes for a clock pulse to propagate from one side of the chip to another, that's pretty significant at that picosecond timescale. And you start to get various sort of digital errors. So you have to play quite a lot of tricks if you want to get much faster than the base clock speed, which is 40 megahertz in this case. There are basically very clever ways which make the data, of course, way more complicated. So you then have to figure out how to decode it. So just to get this data stream out and to get to an image is quite an ordeal. But one of the terms I've used is events. And there's an important distinction here between events and electrons. So in all of these direct detectors, what you find is you have your very fast, high energy electron coming. So that's that blue line coming from the top there. And in this sort of cartoon, you can see that this fast electron is scattered about and it hits several pixels and it deposits its energy as charge into several different pixels, which are then read out by the electronics and time-stamped. And it's kind of interesting because you can see this for a single electron here. So if I can start this movie, this one actually works. This is a single electron hitting the detector, and you can see it sort of splashes across a few pixels over some time interval. I think these are fast ticks, so this is some fractions of a nanosecond. And there's a whole bunch of things when you think about this that are interesting. And your incident electron coming in a few hundred keV is moving at a significant fraction of the speed of light. So it's actually going through your detector way faster than your detector can read it out. And as it's generating charge in different parts of the chip, the order in which they're read out are not necessarily the order in which they happen. They're the order in which they reach the readout electronics. So it tells you quite a lot about how your electron was traveling as it's deposited into the chip. So this is a slightly rougher version of that first example, where you can see that each electron hitting our detector is actually splashing over a few pixels, and it's exciting, this cluster of pixels. And so you have to then group them into clusters somehow. And this is actually quite a fruitful area for ML at the moment, because it's really a problem. It's very simple. It happens a lot. You don't care too much if every single case is exactly attributed right, but you do want the overall distribution and the overall inferences to be correct. So I'm using a much simpler algorithm at the moment rather than AI, but you can go through, you can cluster, so events that happen at a similar time and that are not too far apart belong to the same cluster. And when you go through that process, you can start to integrate how much energy was deposited by each electron, and you can find, you have this great big peak, which is one electron at a time hitting the pixels. Depending on how big you let your clusters grow, you can perhaps have more than one electron hitting at a time. And there's also this interesting escape peak. So this is electrons that don't deposit their whole energy as charge into the detector. And this happens in any sort of detector, really. And what do you do about them? Do you ignore them? Do you count them? There are still some ongoing problems with that, but normally these happen and they just don't register in your detector and you never know about them. But you can start to see that now. But doing this for every electron is this huge flood of data. So this clustering problem is quite interesting. If you think about it, you have these clusters, and that's what my little cartoon is indicating there. This is a series of clusters which are different events, and none of them are actually overlapping. But however you look at it, it always looks like some of them are touching. So you have to have some algorithm which can separate those, and depending on whether you have those very small localized events, which are electrons, or whether here these are actually cosmic rays, just the background radiation in the lab or coming from the sun, which excite multiple pixels, you can sort of start to improve your algorithms to say that these clusters, which happen over some finite spread, all belong to the same event. And so there's another good use case for AI ML there. So I mentioned events that are about the same time and close to each other. So how do you determine what those phrases mean? And so the way we were doing this is we were looking at the autocorrelation of events that hit the detector. And so this, I've just plotted out the autocorrelation function of selection of events. So this is at 100 kilovolts, and you can see that the average event really is sort of spreading out over a few pixels as you increase the energy to 140, 170, and then 200. 200 there. You can see these clusters spread out as the electrons have more and more energy inside it. So you can use that sort of thing to determine what's likely to be one cluster or what's likely to be multiple electron events. It increases reasonably linearly. If you start looking at the statistics, once you get rid of all those sort of digital problems that we mentioned earlier, you can see all kinds of interesting things. So this, in the top right, this is actually a histogram of the time between electrons. And what you can see is that when you're doing your electron microscope experiment, you're really firing electrons through your sample every few nanoseconds. And it's kind of an interesting way to conceptualize electron microscopes. So, okay, we're doing this, it's multidimensional data generation. So if you think about it, our detector now has many pixels. A lot of detectors are 1K by 1K pixels or 2K by 2K. These timing-based pixels are still probably around 512 by 512 pixels, but you can either tile them or you can interpolate a little bit, looking at where the center of those clusters hits. So you can have many more pixels on the detector. Of course, you can do this for every probe position in your STEM image, so you get your multi-dimensional data set. Remember how we were talking about those four-dimensional cubes at the start? You can integrate over different parts of that, and just in exactly the same way as you saw the graphene example, you can form a variety of virtual detectors and image, at different angles. It's interesting in this case because you can tell the sample, this was just a sort of test example I did. The sample was not very well tilted, and the tilt axis is actually somewhere up towards the top left corner. So it's kind of interesting, but it's actually a huge amount of data. So that example was just the first data set I tried to get. So I was doing a 10-second STEM image at about 10 microseconds per position with 1K by 1K probe positions. But with a bit of, processing and interpolation, you can interpolate each camera virtual frame that you reconstruct from the events to 1K by 1K pixels, let's say. So that gives you a terabyte of bits. So even if you're only storing 8 bits per pixel worth of information, you've got a terabyte of image there in 10 seconds. So in this example, you can see the event-based storage is a lot more efficient because most of those pixels are just going to be zero, just saying, oh, an electron didn't hit. But, so there are some compression games you can play. But the important point is this is tens of gigabytes of data that are arriving in a second or so. So should say we have a machine which has 500 gigs of RAM, and I managed to make that crash a few times by running out of memory. But, just as this is an AI workshop, this slide is entirely generated by AI. I just explained my problems to it and said, give me a slide that shows it. So it has a few weird choices of words, but it's actually really good. And it shows some of the problems. Is if you think about the data rate coming out of this detector, you can't even put it into memory fast enough to keep up. So they do a fairly clever scheme where they give it to different processes and they chunk it out to different processors essentially and put it into different bits of memory. But then you have to stick it all back together again somehow. And that turns out to be the most annoying step in the processing, I think. When you go through this, you can get your different sorts of images. Just as I'll try to end on one sort of practical sample that we were interested in for sort of real scientific images. This is our HADF detector image at the left. And of course, my Python library and Neon seem to define their coordinate axes the wrong way around. And the other three images are just different low angle ADF or bright field images generated from different parts of that data. You can play all sorts of other games as well. So in that example, I was doing 60 microseconds per probe position, but you can take that data and you can divide it up finer because remember, you've got the timestamp now after clustering for every electron. So you can divide it up into time bins. So what I've done there is I've divided each probe position up into 10 6 microsecond bins. So in that little sequence of images that you just saw, each frame, each pixel was recorded 6 microseconds after the same pixel in the preceding image. So is that time results then? Almost. But kind of interesting. And then, yeah, you can reconstruct different sorts of images. But, okay, so sticking with this sample that you just saw, this was a tantalum disulfide sample, which we were looking at and because it has an interesting charge density wave. So this is one of these 2D materials, similar sort of structure to the like those MOS2, those sort of layers that you saw again in the previous talk. But this does some interesting things because it's not very happy in its sort of standard form. Some of the atoms want to be closer to each other, and there's some sort of interaction between layers. So at different temperatures, it undergoes different sorts of reconstructions. There are different forms. And one of the nice things with this is that it has some charge density waves that are actually stable at room temperature and maybe even have some neat technological applications for things like memory storage or switching. And as you heat it, it goes through various other different phases. So we wanted to try doing this with some time resolved data. So we went to diffraction mode. If you look at the diffraction pattern from these things, as we heated it, you can see the diffraction pattern change. So if we go to a slightly different part of the sample, this was an early attempt at decoding, so it still looks a little weird. But again, as I heat it, you can see the main spots, the Bragg spots, are staying in the same place. And you see there those little satellite spots. And as you heat it, you can see them moving around. It undergoes some sort of phase change. So this is why we're trying to look at it with a fast detector, is what's happening to these transient modes. So, okay. Here's a sequence, courtesy of our trusty intern who took some of this data and was processing it. There we go. We can start. So what I was doing here was I linked the microscope to a Keithley and we were ramping the temperature up and sending synchronization pulses to the detector so it would know when we're at different temperatures. And then as we heat this sample, I went through several different heating and cooling cycles to see how repeatable it was. And you can see those little satellite spots are moving around. And that's as this material is undergoing its phase change between those different states, and then it's heating it up, cooling it down. And this was looking fairly repeatable. And it's interesting because you get this data and you're recording this in this case, it's just standard diffraction data, but because it's all time-stamped, you can go back and rebin your data to try and get enough signal to noise. So you can try and look at how your phases are changing as you change the temperature. So this was actually 3 heating and cooling cycles that I've done here. And there's several interesting things, one of which is that I was heating or cooling continuously on a ramp, yet the actual phase changes are very sharp, and different phases perhaps are changing at different temperatures. And there's also a difference in the amount of each phase that's generated. So it's a fairly reversible process, but not exactly. Sometimes these things are coming back to different phases. So just to end, I'd say that as you heard a bit about some of the scripting platforms that are available for the different microscopes. If you're using one of the Neon microscopes, there's a Neon Swift platform, and that's completely open source. And you can delve into its source code and enjoy that. And it's actually open, so in principle, you can put it on other microscopes as well as the Neon instruments. Apparently, there's one place which does have a Joel that they run using Neon Swift. Again, using the power of interns, you can write your own plugins because it's all open source. You can figure out how to do this. You don't actually have to get permission from the manufacturer or get special, keys to be able to install a feature or be allowed to use part of your microscope. You can just source code and you can go back and you can figure out how to add in a live display from your new detector, which you just got. So I would definitely suggest, if you're interested in this sort of open source microscope coding, that the Neon Swift is a good resource. And so with that, I don't think I overran too badly, but I'll stop talking. So thanks for listening.